because we're live doesn't mean we're like live immediately. There's a 30-second lag or something like that. All right, it's still not up.
Yeah, I just got a page
Something
not
like that.
available.
There we go. All right, it's still not up.
Yeah, I just got a.
Okay, so volume is working. I just need to get it out of this mode. Default view. Good. Now we got chat. Cool. When you were looking at YouTube, you said page is not available?
It came back up. Yeah,
Okay.
I had to get out of it and go back in.
Cool. So, blow up this window. Cool. There we go. I guess we'll give it a second to see what's going on, and then we'll be cool. Let me know when you're good.
Still not up for me. I feel like everything's been on like super duper delay lately.
Yeah, you're not wrong.
Nope. Still not there.
Wondering if I should shift my camera one way or another. Is that better or worse? A little better, actually. Still nothing?
Yeah, no.
Wow. You want
Keep
the link?
refreshing.
I'll just send you the link. That might make life real easy.
Okay.
I don't know why it doesn't go sometimes, but alas, sometimes that is what it is. Is that better?
I'm not there yet. It's loading. Okay. Yep, there it is.
All right. Are we
But it's
talking
still
and all
loading
good?
now. It's still loading up. All right.
Are we taking final exams this year? Mr. Parks. No, you're not.
Okay. I think I'm good now. Well, now it's refreshing itself.
Yeah, there are no exams for this class. Other classes, I'm not exactly sure. There might be some little things here and there, but
I think in general, no final exams.
yep. All right. Well, we have one Brady in the chat. That is enough for me to think it's time to go.
Yeah. Might
All
as
right.
well.
Yep. All right. So, hello, folks. It's been what, maybe a week since we last talked. We were looking at the plates. We were looking at the plate boundaries. That's what your homework was on. And so today we're going to get into what happens other than the plate boundaries themselves, right? We saw the big scale, like how plates interact, but there are smaller scale things that happen when the plates come together or go apart. We'll be looking at a lot of things that happen when the plates are doing these motions, but they are something we can take like pictures of. They're not like these huge things that we're not really aware of. So that's deformation. And then from there, we're actually going to go into earthquakes, what they are, how they happen, and that sort of thing. So it's a little bit of a longer presentation today, but again, it's going to be what we missed out on Monday. Since we couldn't be here on Monday, we were in the classroom cleaning things out. And so that's that. So let's jump in. So deformation. So there are really two different types of deformation we're going to take a look at quick. you are going to have a project about earthquakes and volcanoes that is coming up, and so we figured it's probably good to talk about faults. Faults are associated with earthquakes because they are the place really where earthquakes get their energy and such from. So what are faults? Faults are fractures or cracks in a rock formation, and they cause a weakness where rocks tend to move or slide. So you can see in the animation there on the bottom right, because there is that fault, that cut, that fracture, that whole piece of land slides, and think about it, that is rock, it's real heavy. When that slides, there's a lot of friction, there's a lot of weight moving, so that's what causes that small shake in this case, is that along that fault there is just all this energy being released as the rock breaks and slides. So this is what we would consider a normal fault, where one section moves down relative to the other section, and we'll see that there are two other types of faults. So again, all a fault is a fracture or crack. It's like a cut. It doesn't have to be that smooth. It usually does actually look like a line. I was over in California in the original Bat Cave for the show from the 1960s one, if you're familiar. It was pretty cool. But inside there were a whole bunch of faults. There were a whole bunch of these lines going across where things had faulted in the past. It was pretty cool. But they just are places where rocks can slide because they're cut apart from each other. So here's a picture, and you can look at the pattern and see that they don't line up. But if they were in a different position, they definitely would. If you are looking here at this large section of light color and then these two gray, you can see here there's that same lighter color with those two lines of gray. So one had fallen relative to the other one. So this would be our normal fault. So whenever the patterns don't really match up, that's a good indication you're looking at a fault. And you can see the line is pretty clear as to where that fault is. Moving on. So a reverse fault is, instead of one section falling down, it's one section being thrust upwards. So it's the same idea, except here, instead of something falling, one is being pushed up. So you will get that same type of line where the fault, this cut in the rock is, and you'll see that one section is pushed above the other. So here you can see this copper kind of rusted looking section is definitely, we don't really know the scale, but presumably a few inches above the other one. But think about that. If the ground underneath you went up a few inches, you would definitely feel a huge amount of energy from that, right? That would release some kind of quake. So these are the smaller earthquakes, these tiny little adjustments, but we'll get into the bigger ones later. So that brings us to the last one, the lateral fault. So this one, instead of one moving up or one moving down, this is where they are grinding alongside each other, kind of like a transform boundary, and that's where they happen, right, at these transform boundaries, and they are sometimes then actually called transform faults. So they're sliding, they are shearing. Ooh, let me silence my phone. Sorry about that. They are sliding past each other and they are grinding. And you can actually see in the picture here that the fence doesn't line up, the river actually gets shifted. It definitely changes the area around it, not so much up and down, but can make things look like they don't match up anymore. There's actually a couple interesting photos I found of where these lateral faults have messed up. This looks like it was some kind of water drainage area made of cement, and you can see it's totally off to the side from where it should be. And then I have another picture where this fence looks like the person who built it kind of didn't know how to build a fence. Well, this is because there's a fault running through the bottom here, and it's actually made the fence not line up anymore. So this isn't somebody who just measured incorrectly. This is a fence that was shifted due to one of these lateral faults, these transform faults. Pretty cool pictures, though, I think.
Absolutely.
I mean, just imagine if your house was in the middle of one of those. That'd be terrible.
Yeah, we can rip it apart.
Yeah. So those are faults, basically, right? You've got the left and right, and then you've got the up and down ones. The normal, the reverse, also called a thrust fault, and then the transform, also called strike slip. Not anything you need to memorize, but just understanding that, like, on a smaller scale, there are these things that we can actually see in the rock itself with these different faults. And they might reference them when they start talking about earthquakes later on. So, the last deformation thing that we'll talk about is folding. So if you have two plates that are colliding together, we mentioned that you can get this like rippling where they crumple up, almost like a piece of paper. When you kind of push it, it makes those weird bendy kind of looks, right? I could take a piece of paper and I could make it straight, and then I could push it together and it starts to fold, right? Folds in at the weakest parts. So the same thing actually happens to rock, and we can get these synclines and anticlines. They're basically just, do they go up or do they fold down? But that is literally like layers of rock that have been squished together, and so they buckle. Next time you are driving on a highway and you know that the highway is like cleared out between some sort of, mountains, take a look at the rocks. It's not always that you see it, but if you have a good chance or I should say you will have a better chance of finding something that looks like this if you're looking at those exposed sections of rock. And again, it doesn't always happen. It needs to be a place where there's been this pushing together, but mountains we know are formed from that. So again, if you're ever on the highway looking at rock formations that are exposed, you may see something similar to this, and you'll know now, oh, that is crustal deformation. It is folding. Didn't just form in a cool wavy pattern.
Right. Keep in mind you won't see it so much here in New York, but if you're driving in other states that are kind of prone to get earthquakes and stuff like that, then that's where you would see it more.
Yep, definitely not on Long Island, that's for sure. So, and this is just a way to remember it if you find this really cool, that the anticline looks like an A, right? The peak of it is at the top, so it's like A for anticline, and then an S here, like smile. Some people say, like a smile, the way it curves downwards for syncline. Just some ways to remember it. So that brings us to our last thing we want to talk about before we get into earthquakes, which are hotspots. So we were talking about the different types of plate boundaries. We were talking about where you can find volcanism in the last time we met, but we didn't really get into a hotspot and what it is. So Hawaii has volcanic activity, but it is not on a plate boundary. How could that be, right? You think, okay, there's got to be some kind of plate boundary so that water can get dragged down. You've got that volcanic island arc or volcanoes on one side of a convergent boundary. How is it that Hawaii has volcanoes if it's in the middle of a plate? Well, the answer is these hotspots. So, a hotspot is a portion or spot of the Earth's surface which experiences volcanism, and this may be caused by a rising mantle plume or some other cause, and it a volcanic hotspot is where lava pushes up from under the mantle and creates a volcano. What does this mean in simpler terms? This means that underneath the plate there is an area that is really, really hot, and hence hot spot, and it generates magma, which will eventually become lava, and it burns its way essentially through the plate and gets up to the top. So this is an isolated spot. This isn't like a long string. It's just a literal one spot that this happens for reasons that we're not fully understanding of. It's just this super hot area that keeps lava flowing. And so that is how Hawaii formed, how all the ancient islands formed, and why we still get eruptions today. We had one, last year, was it? The one where there was like a huge eruption and they were saying that it was raining acidic rain that was as acidic as battery acid. I think that was last year, right? Or was it 2 years ago?
Last year or the year before?
Yeah.
I don't quite remember.
But that is how the islands were made there, is that you've got eruptions, they bring out this hot rock, it solidifies, and you get new land masses in the middle of the ocean. So that's all from just simply this part of the asthenosphere that is so hot, comes up through the crust and just forms enough rock that you get islands. It's pretty cool. So how it works is, over time, and right, the Hawaiian Islands are like a chain, you've got this spot that doesn't move, but you have the plate that moves over it. So originally it'll make one big volcano, and the plate will move. And over time, this right here, number one, is going to move away, and it's not going to be fed any more lava, so it's not going to grow. And so over time, that'll break down and get smaller and smaller. So the place that's over the hot spot now is going to grow and look very similar to the original one with this little bump behind it. And so over time, as this plate continues to move over the hot spot, it'll make a whole series of these little islands, with the island that's over the hot spot continuously growing. And so we get this huge chain of islands that eventually will perish, and that's why we don't actually see all of the Hawaiian islands that have ever existed. There's actually more that are underneath the ocean that we don't see and people don't live on because it's underwater, and they've just over time been ground down by the water and the wind, so they don't exist anymore, so to speak. But it's pretty cool that you have this continuous mountain or volcanic island arc being formed from a single hotspot. So that's why there are those islands and why they look like they're in a line, because that's the way the plate's moving. All right, that brings us to, whoa, didn't want to play this video. Moving forward, that brings us to earthquakes. So what is an earthquake? An earthquake is the vibration or shaking of Earth's crust caused by rapid movement of rocks in the lithosphere. Now, we had mentioned before, a lot of the movements of rocks are very slow. This is the one time, or one of the few times, I should say, that it is not a slow movement. And that's why so much energy is generated and why we feel like these huge tremors, is because it is a rapid movement. So this occurs along faults, those cuts in the rock, at or near Earth's surface along the tectonic plates, and the shaking is caused by a release of energy in rocks beneath the surface. The best way I could describe it to you is similar to the breaking of a pencil. So you have a pencil, and if you start to push and push and push, a lot of energy gets caught in that pencil, and eventually you get it to bam, right? You get it to break. So, oh, sorry, pencil. Anyway, that is kind of what happens where these plates get stuck next to each other. One piece of the rock gets caught on another one, and they build and build and build and build, and then there's that break, that release of tension, and it'll re-grab onto something else, right? It's not just going to fly off forever. It's going to grab onto another part of the rock where it's jutting out. They'll get caught up, but that huge shift is that rapid movement that causes this release of energy and causes the shaking that we're accustomed to. Or, well, we aren't, but the people that live by boundaries certainly. They're used to it in some small part. I certainly have not been in an earthquake like that at all. The only earthquake I've ever been in, I mistook for my brother running around the house. Just small little shakes, nothing crazy.
No earthquakes for me.
Yeah, they're not very common here. And now that we'll see where they're really coming from, you can figure out why by the end of this lecture. So that's a video. You guys can watch a whole bunch of earthquake videos and what it looks like to be in an earthquake on YouTube. Just search it right up. But we're going to talk about now one of the things that's important for understanding earthquakes, which is the different waves that are given off by the shaking itself. So there are two waves that are really, I guess, the most helpful in trying to figure out where an earthquake is coming from, or where its point of origin is. And we'll get to those terms later as to what we call these things. But there are two waves that we really care about because they help figure that out. The first is the P wave, or the primary wave. It's the fastest wave and the first wave that actually gets to you if you're, feeling an earthquake. So they are compressional. They're kind of like an accordion or like a slinky. So if you look at that animation, you'll see that they squish together and then kind of unsquish. So again, it's like that push-pull motion, or like squeezing. So they move very quickly. They get to our detection first, and they're the first, like, hey, you're having an earthquake. Luckily, they are not that damaging. So it's like the first baby tremors, and then that'll lead you into the secondary waves. Now, these are the ones that are going to cause a lot of damage. They are kind of like, like when you're doing the wave with your arms. So they're going up and down. And that is definitely going to shake foundations, shake the earth in a way that you feel a lot more. Interesting part about these is they don't travel through liquids, and obviously since the P wave is first, the secondary wave is second. So it is a little slower. So we get a little bit of a tip, hey, you've got an earthquake coming, and then the secondary wave comes sometime after that. Biggest issue is if you're really close to where the earthquake occurs, the time between those two is not so great. If you're kind of far, you might have a few minutes before the actual S waves kick in. Get to that in a moment. So we were just saying that the S waves don't travel through liquid, and that's actually one of the coolest things that we figured out because it helps us learn about what's inside of Earth. We've never gone down into the core, but we do know that S waves, if we know where an earthquake has happened, never make it to the opposite side of the planet. The reason being is that the core, right, we have a liquid part of the outer core, so S waves just don't go through it. And the P waves get directed around it, but they definitely can get some of their energy through it. So earthquakes have actually been the thing that have helped us figure out what all the stuff underneath our feet looks like, even though we've never actually seen it. Super cool. So there are a few other waves that are related to earthquakes. You've got the L wave, which instead of going up and down is kind of this left and right motion. It's just another way that things can travel, and this does also lead to some damage. And then there are some, again, small other waves that are associated, but the real big ones that we're focused on are the P and the S waves, since they're the indicators and they help us the most with trying to figure out where stuff is. So how do we actually figure out where these things are and how strong they are? It has to deal with a seismograph, which is this instrument here. You've probably seen it if you've ever been to like a science museum or a planetarium or something like that. It's got this little needle with ink on it, and it goes across paper, and it feels or senses the tremors and starts to shake violently if there is a shaking on the Earth around it. So the seismograph is an instrument used to detect and record earthquakes, and the seismogram is the actual document that it produces, the paper with the tracks on it. So that little roll of paper is like always spinning, and you can pick things up with that. Now these are pretty cool too, because if you've ever been to a planetarium or something like that, if they have it really finely tuned, if you were to go near it and start jumping and making a whole bunch of shaking by the instrument, it should pick it up. So next time, you know, when things are open again, if you happen to be at like a planetarium or a science museum or just anywhere that have one of these things, play around with it. See what it's like. This is just a video of somebody doing exactly that in the Griffith Observatory. If you've ever seen the movie La La Land, I was actually there. I played with this one specifically, which is why I brought it up. So, when you're reading this, you will see that there is the first smaller waves that come in. Those are the P waves, followed by the really, really big waves. And here, there wasn't much time. This is probably exactly where the earthquake occurred. There was only 5 seconds. 5 seconds between when they got the P waves and then they got the S waves. So they got those first tremors, and then 5 seconds later they got hit by the earthquake. That's not a lot of time to plan. So if you're really like right by where the earthquake happens, you're kind of out of luck. You better, you know, have your senses with you and get under a desk and do all those maneuvers. But if you are farther away, again, you'll have maybe, you know, somewhere between 1 to 10 minutes, maybe 1 to 20 minutes if you're really far away. But our detection is such that that's the time frame we have to prepare. Not a lot of time.
No, not at all.
So a few more vocabulary words associated with earthquakes. The focus is the point where the earthquake is actually originating from. Like we said with the pencil, somewhere along the faults, you've got these things that are pushed up against each other, that they're caught, and then they snap or they break off, and then you get that shift. Exactly where those two things are generating all that energy is the focus. But the thing is, when we're looking at where earthquakes happen on a map, well, you can't really see into a map, right? We don't have 3 dimensions that we talk about things kind of like this picture. So what they have is they have an epicenter, which is a point on the Earth's surface above where the focus is. So this way, if you're looking at the top of the map, you can go, oh, the epicenter was on New York City, right? You can say where it is, and then you could say, oh, and it was, 500 feet down or something like that. But this helps us communicate where, in terms of the locations that we're familiar with, that these things have happened. So the focus is the exact spot. The epicenter is like, you could think of it like the map location. All right. We had mentioned this before, that earthquake waves move through the Earth. One other cool thing is that the denser the rock, so if you've got a really, really dense piece of rock, the waves actually travel faster through it. So just like we were looking at in the energy unit where you saw the pencil in the water and it shifted, right? That's because the water actually slows down the movement of the light going through it, and it changes the way it looks. That actually happens with the earthquake waves as well, where they get deflected or not deflected, but refracted, or bent as they move between these different things. So again, something else that has helped us map out what's underneath our feet without us actually being there. That's just another picture of the shadow zones and how these things can move. Don't worry about it, but it's pretty cool that all these waves can get refracted so much and in such odd directions. And that leads us to the last thing that we'll talk about, which is the magnitude and intensity. So for the magnitude, that's the amount of energy released during an earthquake, so that is an actual number. That's not something we usually talk about all that much, but the Richter scale is definitely something that's more communicated. So it's a scale based on the largest seismic wave generated by the quake. So that's something I think you know like with the different numbers. I've got a picture of that in the next slide. And then a different one that's interesting is the Mercalli scale. The reason it's interesting is because it doesn't use like these exact measurements. It's based on observations. So let's say you're outside and there's an earthquake and you see that your car is shaking but like no glass breaks or something like that. There's like a list of different things that happen that you rate it by. You can figure out what the scale of the earthquake is based on those little tiny observations. So you might have it where it's like you feel tremors but you don't see cars shake. That would be one version of what the energy could be versus if you see that the buildings are swaying. So it's a way that you can on the spot, like if you were part of an earthquake, figure out how damaging it was or like what the energy was. But the problem is that it's as it says there, each viewer can rate it differently based on the things they see. So some areas might have the building swing and some areas might not, or the buildings might be different, like different heights. So it's not as scientific, but it's like a nice little quick figuring out what type of earthquake you're in. I don't know how useful that is, but it's interesting. No final exam. Hold up. I'm holding up. Yeah. No. There's no regents. Is this news? Was this not officially announced to the students? I thought it was.
Maybe not, but just so you guys know, there's no final exams. No regents, no final exams.
Yep. Okay. So here's a look at the, well, this is the magnitude scale. So 8 or greater, right, is like the terribly destructive ones. 2.5 is like the really, really light ones that usually you don't even feel. So we rate these things based on a number scale. I thought I had a picture for the Richter, but I guess I was wrong. Anyway, so that's how they communicate it. Again, the magnitude should relate back to the amount of energy that's released. But I'm sure when you're doing your project, which we'll get to now, you guys have a project that is not due within a week. It's got a little bit more time than that. I think we're giving it out today, and it's going to be due... When did we say it was going to be due? Not next Wednesday, but next Monday? Like next Monday?
First, I'm looking at a calendar now.
You guys have some time to do it.
First.
All right. But the idea is that you guys are going to find a specific event, an earthquake or a volcanic eruption, and you are going to figure out all this information about it, like what was the damage and where was it, what kind of plate boundary, and you might need to use the scales to figure out exactly how damaging it was. They'll probably explain like it was a this or it was a that, but to get an idea of what type of damage that is when you're looking these things up, make sure you just look for that. So if it says if it was a Richter scale, this or that or whatever, look up the Richter scale, see what it says. So there are different scales for these things. But yeah, so we're gonna post that a little bit later, probably sometime today. I would check in if you're really itching to do it, probably by like 3 o'clock. We'll have it posted by then. But just letting you know that that's how that's going. And then since that's a longer project, we won't really be assigning any other work over that time. So if you have other work you need to still make up, make sure you get that in. We're still collecting all the work that you guys, if you haven't had a chance to do, you can still submit. Also, make sure you guys know that our office hours are still up. I know the last few days, given AP exams, I've definitely not been able to go to mine. But today we're going to have them posted, so you'll be good. I think you need to post this earlier. The lecture? Ryan, you can always watch it back, right? That's the great thing about YouTube.
Yeah, not really sure what you mean by that, Ryan.
Or does he mean the assignment should be posted earlier? The first. So you have what is that, like a week and a half? You'll see.
Yeah.
It's not. It's not that big a thing. We call it a project, but it's like if you think of our regular assignments, it's probably like 2 or 3 of the regular assignments in length. It's not like this titanic project. You'll be fine.
No. Think about it this way. If we were in class and we were going to assign you this project in class, it might be something that we did over like 2 or 3 days.
Right.
In the classroom.
Yeah, so, I definitely agree with that.
It's going to look like a lot when you see it, but you just read through it and then you'll see that it's really not super involved. It's definitely something you guys can do in a week and a half. Not
to mention, we still will have office hours, so if you had any questions, you could always come in and, ask them.
Yes, definitely.
But yeah, make sure you have the homework done for tonight. And if you have any questions, come into office hours. Other than that, I think we're all set here.
I think so.
Cool. Well, have a good day, folks, and we'll talk to you soon.
Yeah, have a good one. Reach out if you have any questions.